Hi everyone, today we're going to do lesson 9.6. In this section we are going to solve nonlinear systems of equations. So just a quick remind you, back in chapter 5 we did solve systems of linear equations. This was back in chapter 5, and this is when both of the equations were lines and we were looking to find where the two lines intersect, and that is the solution. We solved these systems in 3 different ways. We solved them by graphing, substitution, and elimination. We're going to do the same thing now in this section 9.6, but these are called nonlinear systems because they're not both lines. Maybe one will be a line, but the second one won't be a line. It might be a quadratic function with a parabola or an exponential function with a curve. So I'm going to show you what I wrote down here. Maybe you should pause the video and copy down what I have here for my notes. This is just a quick notes of how we're going to go about doing this section. So to solve these nonlinear systems, we're going to start by graphing. The solutions again are the point or points of intersection. We have 3 options here for how many solutions we can have. If the 2 graphs never intersect, that's no solution. If the graphs just touch at one single point, that's one solution. And if the graphs go through each other, then that's going to have 2 solutions. So just a quick remind you of how do we graph different functions. Remember, a linear equation is going to have the form y equals mx plus b. And that's slope-intercept form. So to graph this equation, we're going to start by plotting the b, which is our y-intercept. And then you use your slope, your m, as rise over run. Just a quick remind you, how do you graph a quadratic function? Remember, the form is standard form, y equals ax squared plus bx plus c. So to do this, our first step is to find the axis of symmetry. Remember, we use the formula x equals the opposite of b over 2a, and we put that in the middle of our table, and we make a t-table with our values and plot the points from there. Okay, we're going to take a look at example 1. This is coming from the textbook. I'm just going to do the whole example through with you. So let's copy down the equations. We have y equals 2x squared plus 5x minus 1. Right away, this is a quadratic function, I can see, because it has x squared. So because it's quadratic, we're going to find the axis of symmetry using our formula, the opposite of b over 2a. Our b is 5 and our a is 2. Let's plug it in. So we're going to have the opposite of 5, or negative 5, over 2 times 2. We get negative 5 over 4. So we can leave this as a fraction, or we can change it to a decimal. It doesn't matter, whichever you prefer. And then we want to take this number and we're going to put it in the middle of our table here. I'm going to use a decimal just because that might be easier. So now, before I fill in the rest of my table, I'm going to go over to my graphing calculator and I'm going to see what works best for my table. I could just pick any numbers that I want and plug them in here for x's and fill in my table. But I'm going to use my graphing calculator to get these numbers faster. So the first thing I'm going to do is I'm going to go to y equals, and let's type in our equation for just the quadratic. 2x squared plus 5x minus 1. Now, if I go to second table, remember the numbers in your table, the x's go by ones, but our axis of symmetry here is a decimal. So what I can do is I can actually change what my table goes by so that I can see this decimal that's here. So to do that, you're going to do second, and then above the window button, it says table set. So let's hit that, second table set. So the first thing is, where does the table start? At negative 2, and we can leave that because we can always scroll up or down to see more numbers. So you don't need to touch this first one. But this one, the change in the table, that's what we can change. So because our axis of symmetry is 0.25 at the end, why don't we go by 0.25s in our table so that we can see the axis of symmetry. Now let's do second table. And look at that, we can see our axis of symmetry here, our negative 1.25, And let's put this number in. We can just round it to the 10th place because we're going to graph it by hand. We'll put in negative 4.1. So now I'm just going to use the symmetry of the table here. Here's my vertex in the middle, and I'm going to use the integers for the y's just because that's going to be easier for me to graph. So from my axis of symmetry, let's go to negative 1.5 and negative 1. So we'll go around them, we'll get these integers, and then we'll go to the integers of negative 3 and negative 3. I think that's going to be a nice way to set up my graph. So let's do that. So my next x is negative 1.5, will go down, and that y is negative 4. The next x, again, I'm going to use the integer y, so we're going to go to negative 2, and my y is negative 3. Let's do the same thing going up. This will be negative 1 and negative 4, and then negative 0.5 and negative 3. Okay, so we have our table of values. We're ready to graph this. Let's talk about our linear equation now. So our second equation was y equals x minus 3. This is a linear equation because x is really to the first power. Remember, to graph, we need to know the b, which is negative 3, and our m, the number in front of the x, is really 1 over 1. Okay, so let's go over to our graph paper and let's graph this on our coordinate plane. So on my graph paper here, I already have the equations written down, and I have my t-table or my coordinate plane set up here. Let's do our graph. Okay, we're gonna do the quadratic function first. Let's start plotting our points. We have negative 2, negative 3, then negative 1.5, negative 4, then negative 1.25, negative 4.1. So we're gonna just go a little bit more, just a quarter of the way and just a tiny bit below it. Negative 1, negative 4. And then negative 0.5, negative 3. So yeah, this is a small parabola, and that's okay. If you wanted to get more points, you absolutely can. Just go back to your t-table and your calculator and go till you get to the next integer. So our next one was negative 2.5, negative 1. If you want to plot that point, you absolutely can. So negative 2.5, negative 1. And then we can plot its symmetric point. Let's find where the other y is negative 1. It would be 0, negative 1. Okay, maybe that's a little bit better. We have a little more points. We can see our parabola. Now let's connect these points and let's draw our parabola. All right, now we're ready to graph our second equation, which is the linear equation, y equals x minus 3. We're gonna start at the y-intercept, which is negative 3. And then let's use our slope, which we said is 1 over 1. So we're gonna go up 1, right 1, up 1, right 1. And then we can go the other way too, down 1, left 1, and up. You guys see it. This is where they're gonna intersect, down 1, left 1. So let's connect these points. Let's draw our line. And we can definitely see that the point of intersection is this point right here, and that point is negative 1, negative 4. That's our solution to this system because that's where the two graphs are going to intersect. So let's go over onto our paper. I'm going to write down our solution here is the point negative 1, negative 4. Okay, we can check our answer here. We can check this answer by hand. So to check it, we can plug the point into both equations, and it has to make both of the equations true. Let's do that. We're gonna plug this point into each one and see if it works in both of them. So we have our y is negative 4 equals 2 times negative 1 squared plus 5 times negative 1 minus 1. Let's simplify. 4 equals, well, negative 1 squared is 1 times 2 is 2. 5 times negative 1 would be minus 5, and then minus 1. Let's see, negative 4 equals 2 minus 5 is negative 3, minus 1 is negative 4, so this one works. Let's check the second equation. Remember, it has to be true in both of the equations. Let's plug it into the second one. Negative 4 equals negative 1 minus 3, and yeah, this one definitely works. Negative 4 equals negative 4, so it is true in both of them, and I know that this point is the solution because it makes both of those equations true. Okay, let's also use our graphing calculator. We can use our graphing calculator to solve these, and that's actually how the book does it in this example, in example 1. So I want to show you how to use your graphing calculator to get to the solution. But I wanted to make sure you remember how to graph them by hand if you had to. So let's go to